Hello, welcome to the NPTEL online certification course on deep learning. We are discussing about the multilayer perceptron or feed forward neural network. So, in your previous class, we have given an introduction to the multilayer perceptron or feed forward neural network, and we have also started our discussion on training a neural network or the algorithm which is known as back propagation learning. So, in the previous class, we have considered a back propagation learning algorithm or back propagation training procedure for a single layer neural network having only one neuron, that is a function which is having only one output. And while discussing that, we also have assumed that the neuron does not impose any nonlinearity. That means, given the training vector x and w being the weight vector of the neural network, the output simply becomes w transpose x. And because the neural network had only one output, so the output could be either positive or negative. So, if it is positive, then the sample input vector is classified to one class. If it is negative, it is classified to another class. And we considered the case that the training vectors are given as a pair, ordered pair given in the form x I y I, where x I is the training vector and y I indicates the index to the class to which the x I belongs. And because it was a two class problem, so we assumed that y I could assume either a value 0 or a value 1, whereas w transpose x, when I compute w being the weight vector and x being the feature vector or the input vector, it is not necessary that w transpose x will always be either 1 or 0 or 0. In fact, it will be a real number. It may be 0, it may be greater than 0, it may be less than 0. So, our classification rule was that if it is greater than 0, it is belonging to one class. If it is less than 0, it belongs to another class. But coming to the neural network, the output should be either 1 or 0. That means, if w transpose x is greater than 0, the output should be 1, indicating that it belongs to class say omega 1. If the output is less than 0, then it should be truncated to 0, indicating that it belongs to another class. So, that our class index 0 and 1 matches with whatever you get from the as output of the neuron. And in order to do that, we also have seen before that when we have implemented an OR function or AND function or XOR function with the help of neurons, that the kind of nonlinearity that we have used were simple threshold nonlinearity. That means, if w transpose x is greater than or equal greater than 0, we have put the output to be 1. The moment it is less than 0, the output was clamped or truncated at 0. That means, the threshold value was set at w transpose x equal to 0. So, the moment the output of the neuron becomes more than 0, it is clamped at 1. If it is less than 0, the output is set to 0. Now, here you remember that when we talk about the training of the neural network or updating the weights of the neural network, our training procedure makes use of the gradient descent procedure. That means, we have to take the gradient of the error function or the gradient of the loss function, and the loss functions or the error functions are computed based on the feature vectors which are misclassified. If the feature vectors which are correctly classified, for them I do not have to take any action or I do not have to correct or update the weight vectors. But the feature vectors which are misclassified, for them, with them I have to define a loss function or I have to define an error function, and the weights are updated in such a way that the loss or the error is minimized. And for that, in gradient descent procedure, what you do is you take the gradient of the loss function or you take the gradient of the weight function with respect to the weight vector w. And for that, if I want to take the gradient, it is necessary that your loss function or the error function should be differentiable, because the gradient is nothing but a differential operator. Whereas, if I put the output nonlinearity, which is also known as the activation function of the neurons. So, if the activation function of the neurons is a threshold function is not differentiable, because I have an abrupt change at w transpose x equal to 0. Hence, the threshold function is not differentiable, though it is a very, very simple nonlinearity. So, instead of using the threshold function, a sort of nonlinearity which is used is what is the sigmoidal function. We have also talked about the sigmoidal function when we have discussed about the nonlinearity. So, the sigmoidal function is simply given as, say, I can represent sigmoidal of some function s, some argument s is equal to 1 over 1 plus e to the power minus s. So, here you find that as s is equal to 0 at s is, in our case this s is nothing but w transpose x, which is the weighted sum of the feature vector components weighted by the corresponding weight component. Okay. So, s is this. So, at s equal to 0, sigma s is equal to 0.5, which is over here. And as s goes on increasing, say as s tends to infinity, sigma s tends to plus 1, and as s tends to minus infinity, sigma s tends to be 0. So, that is what is given by this particular curve. And at s equal to 0, sigma s is equal to 0.5. Okay. So, you find that as s increases on the positive side, the sigmoidal function asymptotically reaches value equal to 1, and as s decreases on the negative side, the sigmoidal function asymptotically reaches value equal to 0. The other advantage is this is a differentiable function, and also for when s is sufficiently high to be positive, I can consider the output to be equal to 1, and if it is sufficiently low, that is on the negative side, I can consider the output of the neural network or output of the sigmoidal function to be 0, indicating whether the class is omega 1 or class is omega 2. The other advantage that you find that if I take the derivative of sigma, so my sigma s was 1 over 1 plus e to the power minus s. So, if I take the derivative of sigma s with respect to sig s, this simply becomes sigma s into 1 minus sigma s, which is also a very, very simple form. So, you can take the derivative of this with respect to s, and you can verify that actually this is the derivative that you get. So, these are the other advantages or many of the advantages of using sigmoidal function as a nonlinearity or as an activation function of the neural network. Right. So, given this, so again I consider a single output, but now this neuron is with a nonlinear activation function, and the nonlinearity I consider is a sigmoidal function. So, given this, now how can such a single layer neural network can be trained? So, as before, I assume that my training samples are given as ordered pairs x I y I, x I being the feature vector and y I is the class level of that feature vector. Here, when I feed in this input vector x I to this neural network, I get an output y I hat. In the previous case, without nonlinearity, this y I hat was simply w transpose x I, but now I impose a nonlinearity by the sigmoidal function. So, y I hat is now sigma of w transpose x I, right. So, this is my y I hat, whereas the class level for this x I is given as y I. So, as a result, I have an error which is given by y I hat minus y I. So, this is the error if my output y I hat does not agree with the class level y I that is given. So, using this error, I can define again a loss function or an error function, which is nothing but E is equal to half of y I hat minus y I square. So, you find that now the procedure that I am following is a stochastic optimization procedure. If I take the sum of this error over all the samples I equal to 1 to n, the kind of optimization procedure that I will be using is a batch optimization procedure. So, if I take single vectors, it is a stochastic optimization procedure. So, let us now continue with the stochastic optimization. So, my error is given by half of y I hat minus y I square, which is nothing but half of sigmoidal function of w transpose x I minus y I square. So, now if I take the gradient of this error function or this loss function, the gradient with respect to w, you find that the gradient will be given by this. You find that in the earlier case, when our y I hat in absence of nonlinearity was y I hat minus y I square half of this, okay. Then the gradient of sorry, this is not y I hat, this is when my error was E is equal to half of y I hat minus y I square, then gradient of E with respect to w was simply y I hat minus y I times x I. This was without nonlinearity. Now, as we have imposed nonlinearity, which is a sigmoidal function, and we have said just before that for sigmoidal function, if you take the gradient, if you take the derivative with respect to argument, it becomes sigmoidal s into 1 minus sigmoidal s. So, here just before, because of that, if I take the gradient of E, gradient of the error function, the gradient of error function becomes y I hat into 1 minus y I hat, where this y I hat is nothing but my sigmoidal, which is sigma times w transpose x I, and the other one term simply comes from here. This is basically gradient of E with respect to w without the sigmoidal function or without the nonlinearity. So, this is the gradient of E or gradient of the error function that we get when the sigmoidal nonlinearity is imposed. And once you do that, now my weight updation rule following the gradient descent procedure simply becomes w gets w minus eta, again the rate of convergence factor, into y I hat into 1 minus y I hat into y I hat minus y I times x I. This is my weight updation rule in case I have a single output layer node or a single layer neuron with only one node, and by assuming nonlinearity of the neurons. Okay. And here again you can compare that this is a rule which is similar to same perceptron algorithm that we considered earlier, hence the perceptron network. So, the network that we are talking about right now is what is known as a single layer perceptron, because I have only one layer in this neural network, and that too I have only one node in the neural network to implement a 2-class problem. If the number of classes are more than 2, then I have to go for more than 2 neurons, but again the number of layers will be 1. So, let us see such a neural network now. So, now I will consider a neural network, again a single layer neural network, but the number of neurons in the output layer is more than 1. That means, we are considering multiple classes, multi-class problem where the number of classes is more than 2. So, here as we said before that I will have 2 layers. One of the layer is an input layer, and this input layer does nothing other than simply passing the input to the output. So, if I take this ith neuron gets x I, which is ith component of the feature vector x, and simply passes this to the output. Okay. So, the output of this neuron is also x I. That is what this input neurons does. It simply passes the input to the output, nothing else. It is just for an interface. The actual classification is done by this output layer neuron. And when I discuss this, I also assume that these output layer neurons have non-linearity as activation function. And as we have done before, just in the previous problem, the non-linearity we consider in this case is sigmoidal non-linearity or a sigmoidal function, right. So, if I consider an ith neuron, the output of the ith neuron in the input layer is x I, which is ith component of my feature vector x. Okay. And this x I is fed to the inputs of all the neurons in the output layer. So, in the output layer, now if I consider a jth neuron, so this ith neuron in the input layer is connected to the jth neuron to the output layer via a connection weight, which is wij. You find that when we introduced the feed forward neural network in its totality, we had put an index, a superscript which was k, to indicating the layers, right. So, superscript k indicates that this is a connection from the ith layer, from the ith node in k minus first layer to the jth node in kth layer. Now, since we are talking about a single layer neural network, so I will not use that superscript k, because it is simply connection from input layer to the output layer, that is known. So, this superscript k I will not use for this purpose. So, let us remove this superscript k. So, I have this situation that x I, which is the output of the ith node in the input layer, is connected to the jth node in the output layer through a connection weight x I j. So, every node in the input layer is connected, is feeding input to every node in the output layer or the jth layer. As a result, the weighted sum of all the inputs collected by the jth node in the output layer is given by theta j is equal to wij times x I, where I varies from 1 to d, assuming d to be the dimensionality of the feature vectors. The input feature vector has got d number of components. So, this is the sum of or weighted sum of the inputs, or this is nothing but if I represent all the weights from the input layer to the jth layer by say wj, the weights from all the nodes from the input layer to the jth layer to the jth node in the output layer, if those connection weights are represented by a vector wj, this expression theta j is nothing but wj transpose x. So, I can also put in this vector form, or this is a scalar form, but both of them are same. So, that is the weighted sum of the inputs, and then we said that every neuron has a sigmoidal activation function. So, the output OJ that I am getting from the jth neuron is given by a sigmoidal function of theta j, which is nothing but 1 upon 1 plus e to the power minus theta j. Right. Again, remember that our input vectors are given by x I, y I. where yi is the class node. So, if this input x is said that it belongs to class j, that means we know that what is the output of the jth neuron, which should be the output of the jth neuron when this x is fed to the input of the neural network. And that is what we are representing by Tj, which is the expected output or the true class of the input vector x, which is fed to the neural network. But Oj is the actual value that you are getting from the jth node of the neural network when you are feeding the same input vector x. So, as a result, you have an error which is Oj minus Tj. So, as before, we define the sum of squared error, which is nothing but Oj minus Tj square, because now output is a vector, right. For every input x, I will have, if there are say m number of classes, I have m number of nodes in the output layer, every output layer node will give me some value. So, if this input vector x belongs to jth class, only output of the jth node in the output layer should be equal to 1, all other outputs should be 0. So, that is what is my target vector, and using this, what is my target vector and what is the actual vector that I get, we define what is this sum of squared error. So, again for training this neural network or for learning, I use the backpropagation learning algorithm. For that, what you have to find out is the gradient for using gradient descent approach. So, if I take the gradient of E, which is the loss function or the error function, with respect to wij, which is the weight component connecting the ith node from the input layer to the jth node in the output layer. So, this gradient del E del wij, I can compute this using chain rule. It is del E del Oj, where Oj is a function of theta j, okay, because Oj is nothing but sigma theta j. So, I compute del Oj upon del theta j into del theta j, again del theta j is a function of wij. So, del theta j upon del wij. And through this chain rule, you find that what I get as del E del wij is nothing but Oj minus Tj. Oj is the output of the jth node, the actual output of the jth node. Tj is the target output. So, del E upon del wij becomes Oj minus Tj into Oj into 1 minus Oj times xi, where xi is the ith component of the input vector, or xi is the output of the ith neuron in the input layer. So, this is the gradient that you get. So, using the weight updation rule, using the gradient descent procedure, the weight updation rule for the weight component wij as before will be simply wij is equal to wij minus some constant, the convergence rate eta into Oj minus Tj into Oj into 1 minus Oj times xi. Okay. This is the weight updation rule. So, if you do it for every I and every j, you are updating every component of the weight vectors, which are connecting the outputs of the input layer nodes to the inputs of the output layer nodes. So, once you do this for all ij, so all the weight components, now you find that we have two sets, multiple sets of weights, right, because for every output node I have a weight vector. So, since there are m number of nodes, here instead of a single vector I have a matrix. So, I can put this matrix as W, where W will have say m number of rows and right d number of columns. Okay. where every row corresponds to weight vector of a particular class, right. So, later on when we talk about multilayer perceptron with multiple nodes at the output, very often we will use this matrix convention other than single vector convention. So, this is the weight updation rule or the training procedure for a 2-layer network having multiple nodes in the output layer, right. So, given this, now we can go for training of the feed forward neural network having multiple number of hidden layer nodes and also multiple number of output nodes. So, for that, the network that we have considered was having this kind of architecture, which also we said before that I have an output layer which I put as kth layer, the input layer over here. So, this is the output layer which is kth layer, I am putting it as capital K. This is the input layer, and as we said before, the function of the input layer is simply pass the input vector to its output. So, which we are representing as j as 0th layer, in between a kth layer represented by lowercase k. And as we said before, that we will also assume that from a node I in k plus first layer to a node j in kth layer, I have a connection weight which is given by w I j k. So, this is the convention that I will use. I will also use the convention that in the kth layer the number of nodes is given by m k. So, m k is the number of nodes in the kth layer. So, while doing this, in the output layer which is capital K, the number of nodes will be given by m capital K, which is same as the number of categories or the number of classes we will consider. Now, unlike in the previous case, here I will have two distinct situations. One is, as we said, that we can only compute the error at the output, because there only at the output I know what is the target. I cannot compute error at any of these layers. I cannot compute error here, I cannot compute error here, because here I do not know what are the targets. That is the reason all these layers are known as hidden layers, and this is the layer where the output is visible and the output is known for known classes. This is a output layer or visible layer. All rest of the layers are hidden layers. So, we will see that when we talk about the backpropagation learning of such a multi-layer perceptron or a feed-forward neural network, then we will have a little difference, because now I have a number of hidden layers which I did not have earlier. So, error that you compute at the output, that can directly propagated to the connections between the output layer and the hidden layer just before that. So, here computing the gradient of the error is straightforward. But when we try to update the weights of the layers in between hidden layers, then I have to see that how this error actually propagates to this level, and that is where we will have a little bit of mathematics. So, we will talk about this training or backpropagation learning of the feed-forward neural network in our next class. Thank you.